Hello everyone, this is Azale and today I want to present a fascinating topic in machine learning field called CyCADA, which stands for Cycle Consistent Adversarial Domain Adaptation. This presentation focuses on the concept of domain adaptation, a method that allows models to adapt to new data environments. We'll explore how CyCADA tackles this challenge using cutting-edge techniques. Let's dive right in. Let's start with what domain adaptation is. In machine learning, models are often trained on data from one environment but deployed in a different setting. The challenge here is that the model trained on synthetic data might not work well with real-world images. Domain adaptation bridges this gap, helping models generalize better to unseen data. A practical example is autonomous vehicles. They're trained in simulated but need to perform reliably on real roads under various conditions. In the visuals here, you can see the examples of transforming images across different styles and domains, like converting photos to Monet painting, changing zebras to horses, or altering scenes from summer to winter. These transformations highlight the challenge of adapting models to understand and modify data from one domain to another while preserving the core concept. Before going further, let's get familiarized with the kind of data that we want to work on. Until now, you may have seen many examples of paired image-to-image translations. This works well when we have clear input-output pairs. For instance, we can use an edge detector to extract edges from a realistic image, and that gives us paired training data, where we know exactly what the output should look like. However, that's only feasible when we have a clear algorithm to generate those pairs. But what happens when we don't? This is where unpaired image-to-image translation comes in, and it's not as straightforward. In unpaired image-to-image translation, we're usually working with two separate collections, or piles of images. Let's call them set X and set Y. For example, one pile might consist of realistic photos, while the other could contain paintings in the style of Monet or Cézanne. Or it could be images of winter scenes versus summer landscapes. The key challenge here is that there isn't a direct match between images in two sets. They don't correspond one-to-one. So our goal is to train a model to capture the general stylistic elements of one set and apply them to the other. In other words, we want the model to learn how to transform images from set X to resemble those in set Y, and vice versa, without relying on explicitly paired examples. Now let's explore why domain adaptation is important. In many real-world scenarios, collecting labeled data is expensive, time-consuming, and sometimes not feasible. Consider medical imaging. Manually labeling thousands of X-ray images require expertise and significant resources. If we could instead use labeled data from a different but related domain, such as synthetic images or images from another hospital, and adapt it to our specific needs, we could have saved both time and cost significantly. Domain adaptation also helps in situations where the target data is dynamic and constantly changing, like in social media analytics or weather prediction. Now let's take a closer look at the visual example to better understand why domain adaptation is so crucial. In the images at bottom, we have different representation of a cat. The original color image, a grayscale version, a silhouette, and edge-detected outline. The bar graphs above show the performance of various models, such as AlexNet, GoogleNet, ResNet 50, as well as human accuracy on recognizing these images. As you can see, these models perform almost perfectly on the original image, but struggle significantly with silhouette and edge-detected images, which have fewer features and less context. Human performance, though, remains high across all variation, but the models show a clear drop. This highlights a key challenge in machine learning. Models trained on one type of data often fail when faced with a new domain that has a different representation. The ability to adapt models so they can generalize to these new visual styles without being explicitly trained on each one is the goal of domain adaptation. This is exactly what CyCADA aims to achieve by transforming data from one domain to another while preserving the underlying content. Now that we have understood the motivation behind domain adaptation, let's dive into two primary approaches used in this field: feature level and pixel level adaptation. First, feature level adaptation methods work by aligning the features extracted from the source and target domains. The goal is to reduce the disparity between these features, often using techniques like maximum mean disparity or adversarial learning. However, these methods can have significant drawbacks. For instance, aligning features alone doesn't always ensure semantic consistency. This means that features extracted from a car in the target domain could be mistakenly aligned with those of a bicycle in the source domain. Additionally, focusing on high-level features might overlook important low-level details, which are crucial for certain tasks such as medical imaging. On the other hand, we have pixel-level adaptation, where we directly transform the appearance of source images to match the target domain's visual style. Techniques like CyCADA have produced great visual results by transforming image to look like they belong to target domain. However, these methods are not without challenges. For instance, while they excel at making images look visually similar, they may not always preserve the semantic meaning required for a specific end task. In some cases, a digit 8 might end up looking like a handwritten 1 after transformation. Additionally, this technique tends to perform best with smaller or simpler images and often struggle with more complex real-world domains. Both methods have their strengths and weaknesses, and our goal with CyCADA is to combine the best of both worlds to overcome these challenges. This diagram illustrates how feature-level adaptation works. Think of training a model to recognize objects, but the images it sees during training are clear and high quality, while in the real world, they're blurry or dark. That's where feature-level adaptation helps. Here's how it works. The input images go through a feature extractor which finds important patterns like shapes and textures. These features then split in two paths. The blue path, as you can see, focus on classifying the object like identifying a car or cat. However, the red path tries to figure out whether the features came from the source or target domain. Now, to make our model work well across different environments, we set up an adversarial game. The feature extractor tries to disguise the features so well that the domain classifier can't tell where they came from. This forces the model to focus only on what's important for the task, making it robust to changes in image quality or style. Now let's move to pixel level adaptation. You can see a clear example of pixel level adaptation in this slide. The images on the top represent the source domain, where we have both the original photos and their corresponding semantic segmentations. The bottom row shows the target domain along with segmentations before and after adaptation. The goal here is to transfer the source domain and the goal here is to transform the source domain images so they visually resemble the target domain. By doing this, we reduce the gap between domains, enabling models trained on one domain to perform better on the other. The before adaptation examples show how the segmentation is misaligned, while the after adaptation examples demonstrate improved alignment with target domain. This approach is particularly useful when we have access to abundant synthetic data but need our models to perform well on real-world data. However, as we can see, ensuring that semantic consistency is maintained remains a challenge, especially when transforming complex scenes. So for that, I want to introduce cycle consistency, which is a fundamental concept used in pixel-level adaptation models like CyCADA. The core idea is both simple and yet powerful. If an image is transformed from one domain to another and then back again, the resulting image should be identical to the original. This round-trip transformation ensures that the model learns to change the style without altering the underlying content. In example here, you can see two generative adversarial networks working together. The first GAN, H to Z, transforms an image of a horse into zebra. The second GAN, Z to H, then converts the zebra images back into horse. The principle of cycle consistency ensures that after this two-step process, the final output remains faithful to the original horse image. This approach is especially valuable in domain adaptation, where we need to change the visual style of the image while preserving their essential structure and meaning. For example, if we're translating images between summer and winter scenes, the landscape and objects must remain consistent, even if the appearance changes dramatically. By enforcing cycle consistency, we can ensure that models maintain both structural integrity and semantic content, which is crucial for tasks requiring precise recognition. Let's wrap up with a summary of the problem. The image here illustrates the challenge of domain adaptation. On the left, we have zebras, and on the right, we have horses. The goal is to transform images from one domain to another, such as converting zebras to horses, while keeping the core content consistent. The main challenge we face is ensuring that while we change the style, we don't lose the underlying content. In other words, we want to preserve the common elements, like shapes and structure, while adapting the unique style elements. This balance between content and style is crucial to making models robust across different domains, allowing them to generalize better to new environments. Now that we've outlined the challenges of domain adaptation, let's look at a solution that addresses these problems, which is our paper CyCADA. It combines the best of both worlds by using feature-level and pixel-level adaptation techniques. On one hand, it transforms the appearance of source images to match the style of target domain, while on the other hand, it aligns internal features to ensure that they are consistent across domains. CyCADA incorporates cycle consistency to maintain the structure and semantic of data. This means that whether we're transforming images or aligning features, we ensure that the core content remains unchanged. The result is a robust model that performs well, even when faced with complex real-world scenarios where data can vary significantly. So here is how CyCADA tackles the domain adaptation challenge using multiple techniques. We start at this left side, the pink section. CyCADA begins with pixel-level adaptation. Here the model uses a generator to transform the source image to target domain. We can see how the source image is stylized to resemble the target domain, ensuring that it appears more similar to target data. This process is supported by an adversarial approach where the discriminator tries to distinguish between real target images and stylized images, as shown in this green part. Next, we move to the orange portion. We have feature-level adaptation. Once the images are stylized, the model extracts features and aligns them using adversarial training. This helps reduce the feature difference between source and target domains, making the model more robust. Now let's focus on this red cycle, which highlights one of the CyCADA's key innovations. If you remember, we mentioned cycle consistency. The idea was if you transform an image to target domain and then transform it back to the source domain, the result should be nearly identical to the original. The cycle consistency helps preserve the structure and content during the adaptation process. Additionally, we have a gray part, which uses semantic consistency to retrain task-specific information. For example, if we are segmenting objects, this step ensures that the model prediction remains accurate, even after adapting styles and features. This prevents issues like label flipping and maintains consistent results. Finally, CyCADA integrates all these techniques with a pre-trained model on the source domain, ensuring the model performs well before adapting to target domain. Together, these techniques, pixel adaptation, feature alignment, cycle consistency, and semantic consistency, create a robust system that preserves crucial detail while adapting between domains. So enough for the explanation. Let's jump to experimental results. This table provides a clear breakdown of how each component of CyCADA contributes to its superior performance. As you can see, the full CyCADA model achieves an accuracy of 90.4%, significantly outperforming models that lack key elements, like cycle consistency or semantic loss. This demonstrates that combining pixel and feature adaptation along with enforcing semantic and cycle consistency leads to substantial gains in accuracy. Further, we can see in this picture A that without semantic loss, the model satisfies both GAN and cycle constraints. Translated image matches the amnesty style, and reconstructed image matches original. However, the translated image loses its semantic. For instance, an 8 becomes unrecognizable in the amnesty style. However, in this part, we would see the effect of removing cycle consistency. With that, we mean there's no guarantee of accurate reconstruction back to the original one. Even with semantic loss, issues like label flipping still occur, showing why both losses are essential for maintaining correct translations. Here we can see how CyCADA handles domain adaptation between synthetic GTA5 dataset and the real-world cityscapes dataset. In column A, we have the original GTA5 images. You'll notice how vivid and saturated the colors are, with rough textures, especially on the roads. These characteristics are common in game environments. When we adapt these GTA5 images to match cityscapes, as shown in column B, we can see a clear reduction in saturation and a smoothing of textures. The roads, which were rough in the original GTA5 images, become more uniform, better reflecting the real-world scenes captured in cityscapes. Columns C and D show the reverse process, where we adapt cityscapes images to fit the GTA5 style. This showcases CyCADA's flexibility in handling both directions of domain adaptation, making it ideal for applications where synthetic data needs to be adapted for real-world use and vice versa. So thank you for your attention. Any questions?